Imagine you're building a spam filter. An email lands, and you'd like more than a blunt verdict of spam or not spam. You'd like a number, something like the probability this message is spam is 0.94. To get there, you compare the classes by their probability, given the words you see. Naive Bayes builds those probabilities from two simple ingredients. You can count straight off a pile of labeled emails. The prior, how common each class is, and the likelihood, how typical each feature is inside a class. That, plus one bold assumption, is the whole method. Start from Bayes' theorem, the engine underneath. Write X for the features, the words in the email, and C for a class. The posterior, P of C given X, equals the likelihood times the prior over the evidence. To classify, we don't need the exact number yet. We just pick the class with the biggest posterior. That winner is our prediction, C hat. Now watch a lovely simplification. That denominator, P of X, is the plain probability of those words. It doesn't mention the class at all. It's the same number for spam and for not spam. So when we're only ranking the classes, we can drop it entirely. The winner is decided by the numerator alone, the likelihood times the prior. There's one term hiding real trouble. The likelihood, P of X given C. Remember, X isn't a single feature. It's the whole bundle at once. This is a joint probability over every feature at once. If each of D features can take V values, a full table for one class needs V to the power D entries. Put a real number on it. To value features and a modest vocabulary of 1,000 words is to the 1,000th power, a number with 300 digits. No dataset could ever fill that table. Here is the one bold idea that rescues everything, and it's the reason this method is called naive. We assume that once the class is fixed, the features are conditionally independent, and conditional independence lets a joint probability split into a simple product. That fearsome joint likelihood collapses into a product of per feature likelihoods, one honest factor for each word. Look what happened to the cost. An exponential joint table, V to the D, shrinks to a handful of tiny tables, one per feature. The work now grows linearly, not exponentially. Is the assumption actually true? Almost never. The words free and money clearly travel together. Yet, even when the independence is a fiction, it ranks the classes remarkably well. That robustness is why naive Bayes has lasted for decades. Fold the product back into Bayes, and the entire classifier fits on one line. Predict the class that maximizes the prior, times the product of the per feature likelihoods. Give that quantity a name, the score of a class. The prediction is simply the class with the highest score. And if you ever need the real probability, not just the winner, normalize. Divide each class's score by the sum of all the scores. That hands back the true posteriors that add up to 1. Let's make it concrete with a tiny labeled set. 8 emails a human has already sorted. 3 are spam on the left. 5 are ordinary mail on the right. For each, we simply note which words appear. The priors are just the class proportions. 3 of the 8 emails are spam, 5 are ham. So the prior for spam is 3/8, and for ham, 5/8. Now the likelihoods. For each word, count how many emails in a class contain it, over the size of that class. The word win appears in all 3 spam messages, so its likelihood in spam is 1, but in none of the 5 ham messages, so there it's 0. Hold that 0 in mind. Here comes a fresh email containing 2 of our words, free and money. Which class wins? Score each one. For spam, multiply the prior by both spam likelihoods. 3/8 times 2/3 times 2/3. That comes to 1/6, about 0.17. For ham, the same recipe. 5/8 times 2/5 times 2/5. That's 1/10. Exactly 0.1. 1/6 beats 1/10. So the prediction is spam. Free and money appear in ham too. but they're more concentrated in spam, and the product tips the balance. Want the actual probability, not just the label? Normalize. Add the two scores to get the evidence. 1/6 plus 1/10 is 4/15. Divide each score by that total. Spam's posterior is 1/6 over 4/15. A clean 5/8, 62.5%. Ham gets the remaining 3/8. They add to 1, as posteriors must. Now a different email. Win money. Score it, and something ugly happens. Remember, the word win never once appeared in a ham message. So its likelihood there is exactly 0. Multiply the ham score, and that single 0 drags the entire product to 0. One unseen word, and the classifier calls this email flatly impossible as ham. That's far too harsh. A single missing word should nudge the odds, not obliterate a whole class. This is the zero frequency problem, and it's the reason raw counts alone are dangerous. The fix is beautifully simple. Laplace or Advent smoothing. Pretend you saw every possibility one extra time. Add 1 to every count on top, and add v, the number of possible values, to the bottom. Here a word is either present or absent, so v is 2. Watch the poison drain away. The 0 for Wingivenham becomes 0 plus 1 over 5 plus 2, 1/7. Small, but no longer 0. Every other likelihood gets the same gentle bump. Rescore that win money email with the smooth numbers, and the ham score is now a small but honest 15 over 392. A real chance, not a hard 0. Spam still wins, and rightly so. But ham is back in the running. Smoothing keeps the model humble. Nothing it never saw is ever declared truly impossible. One more practical worry. A real email has thousands of words, so the score multiplies thousands of small probabilities. Their product shrinks towards 0 fast, small enough to vanish inside a computer. An underflow. The cure is a classic trick. Take the logarithm. A logarithm turns a product into a sum. So the score becomes the log of the prior plus a sum of log likelihoods. Friendly, well-behaved numbers. And because the logarithm only ever increases, it never changes which score is largest. The winner is untouched. On our spam example, the log scores are minus 1.8 against minus 2.3. Spam still on top. The likelihood term is the one knob you tune to your data, and it comes in 3 common flavors. Multinomial naive Bayes uses word counts, how many times each term appears. It's the workhorse for text. Bernoulli naive Bayes cares only whether a word is present or absent. A yes or no per feature. Handy for short documents, and exactly the presence model we just used. And Gaussian naive Bayes handles continuous features, a height, an income, a sensor reading. There the likelihood is a bell curve, a normal distribution fitted per class. Same rule throughout, only the likelihood changes. Your turn, and you can fully solve this one. A single word decides. You're sorting reviews into positive, class A, or negative, class B. 60% of reviews are positive. The word great shows up in half of positive reviews, but only a fifth of negative ones. A review contains great. Which class wins? Pause, compute the two numerators, and compare. Here's the walkthrough. Score A, the prior times the likelihood, is 0.6 times 0.5, which is 0.30. Score B is 0.4 times 0.2, which is 0.08. 3/10 comfortably beats 800ths. So the review is positive. And if you normalize 0.3 over 0.38, the probability of positive is about 79%. Notice the prior did real work here. It lifted A even before the word was counted. If you got that, you've genuinely got naive Bayes. Trap 1. Dropping the prior. Compare the whole score, prior times likelihoods, not the likelihood product on its own. With imbalanced classes, The prior can decide the answer by itself. Trap 2. Mixing up the independence. The naive assumption is independence given the class. It does not claim the features are independent in the population at large. Free and money are plainly linked overall. Trap 3. Fessing over the denominator. For the decision, the evidence P of x cancels. Compare numerators. You only need it when you want an actual probability. And trap 4. The two that break real code. A zero likelihood kills the product. So smooth it with admin. And thousands of tiny factors underflow. So add logarithms instead of multiplying. One last caution. Even when the winner is right, the raw probabilities can be poorly calibrated. Trust the ranking more than the number. Let's lock it in. The one bold move. Given the class, treat the features as independent, so the joint likelihood becomes a product. That turns Bayes into a fast classifier. Predict the class with the largest prior times product of likelihoods. Normalize those scores, and you get real posterior probabilities. And to fixes make it practical. Advent smoothing so no unseen feature zeros a class. And log probabilities so nothing underflows. Naive in its assumption, but sharp, fast, and genuinely useful. That's naive Bayes.